What I want to do with this video is just briefly give you some starting tips for this kinetic diagrams assignment that we got, that you should be getting in class or have maybe already picked up. I just want to kind of walk you through a couple of tips to kind of get you thinking about how to use this right so that you can get moving in the right direction. And some of the notes and resources that you've already got that should be helpful in helping you get started. So a couple of things to be looking for. One, you've got some notes from large group, maybe 8 days ago now, as I record this, so a week ago or so. We went through some things with collision theory. You drew out some pictures, and one of the first things Mr. Mitchell went through with you in the notes that day had to do with this. It wasn't titled collision theory that day, but when we hear those terms, collision theory, and you'll see those on the assignment, the reason I'm highlighting it is it starts to show up in places on this assignment as soon as one of the first few questions on here. Let's see, question 12 asks you to use your knowledge of collision theory. So it's something that you're going to see pop up and refer to on here. I just want to remind you what that means, what that's referring to. So collision theory is just really sort of the simple rules that help us kind of understand how reactions happen, when reactions happen, maybe when they don't happen, and the sorts of things that will have to be true in order for a reaction to occur. So in this case, we're really just thinking about any kind of simple planal reaction where A and B are reacting to form, let's say, C and D. If that's going to happen, you have to have particles for A and for B. So whatever substances those might be, you have to have them both, which kind of seems obvious. But those particles also have to collide with each other. So they have to be put together in the same container and allowed to run into each other, whether they're gases or in solution or even just solids that can react with each other. They have to collide. If they don't collide, they can't mix up their bonds and reform new ones to get products like C and D. The last thing that has to be true, and this is a big one, is the collisions between them have to have sufficient energy for the bonds to be broken and rebuilt. So the particles A and B would have to collide. There's something to be said for the fact they have to collide just right. So they have to kind of bump into each other in just the right orientations in order for the bonds to be broken just right, especially in larger molecules. And those collisions have to be forceful enough to break bonds that are there and form new ones. So the good news, I guess, is that not all of these three criteria are met every time particles that could react bump into each other. In other words, for example, in our air, there's a lot of nitrogen and a lot of oxygen. And nitrogen and oxygen can form a number of compounds, one of which would be like laughing gas. Um, Fortunately, I guess, nitrogen and oxygen in the atmosphere that we breathe, those molecules, when they bump into each other, which happens constantly in our air, there's not enough energy in that collision for nitrogen and oxygen to form a new compound. So no reaction occurs most all the time. And that allows nitrogen and oxygen to remain plain old elements that bop around in our atmosphere and give us something to breathe and use and for plants to utilize and so forth. So not every collision has sufficient energy for bonds to break, form, and change into new things. In this case, we're calling them C and D. So that's the first thing to kind of remind you about from large group last week. You'll also remember in collision theory in large group, we went through and showed that reactions have to go through one of these pathways. The idea being that every reaction needs a certain amount of energy. And that has to do with why collisions that don't have much energy don't react. They haven't achieved or accomplished the activation energy, which is a sort of barrier. And we went through this in large group last week to show you that there's a barrier here that shows the higher pathway or the greater sort of slope here, a mountain, that to go from left to right, you have to pass over this great big hill, which is the activation energy for this reaction going forward, left to right, when a catalyst isn't being used, or we can use a catalyst. And a catalyst would take us through a lower energy pathway, which is shown here as kind of the darker blue, lower, sort of more of a hill compared to this large mountain. So in the case of a catalyst, what it does is lower the barrier, it lowers the activation energy. So it allows more collisions that are already occurring to be enough, to have enough energy in order for the reaction to happen. It doesn't create more forceful collisions. It doesn't create more collisions. Using a catalyst simply lowers the barrier that's required for the collisions to overcome. So it makes it easier for them to react. How it does that varies from catalyst to catalyst. So I won't get into that here, but that's what a catalyst does. The other thing that kind of comes into play is if we start messing with temperature. So if we start increasing the amount of energy in a sample of matter, the collisions might be more frequent, but they also might be more forceful, or both. And those greater energy collisions mean that there'll be more collisions that are effective and cause a reaction to occur. So there's kind of some things from large group from last week. One of the things that we went over in the large group slides last week um, show this change in enthalpy, and we had you labeling these things on your notes in large group. Show there's the energy stored in the initial reactants, the energy stored in the products, and then the change in energy from left to right. So no matter which of these two pathways I go through, this final arrow we label as delta H, or change in enthalpy, represents the change in energy from start to finish, from the beginning of the reaction, where there are simply reactants present, to the end of the reaction where there are products present. Again, whichever pathway you go through, this represents the amount of energy that's either gained or lost by the reaction. In this case, it's the energy lost. And I know it's energy lost because it started with more energy and I'm ending with less energy. So that difference, this delta H amount, is being released to surroundings. As heat, as light, as noise, it could be any number of things being spent or released. So as we look at these curves, and you should have yours like this filled in with labels and things, be careful to pay attention to the small differences that are sometimes there. And the idea in some of the questions in your assignment will be sort of drawing curves like these, but now we're going to start adding numbers to them. And I'll go through an example of one like that with you as well. So back on your assignment sheet, the first question on here asks you to fill in the blanks. Well, first, there really aren't blanks, just a lot of spaces where you could write these labels. So fill in and label the reaction coordinate diagram with the appropriate letters. And it says here, notice, not all letters will be used. And that's important because it turns out you can't really use all four of these in a given picture. The reason being, you can't have energy absorbed and released by the same reaction. It either releases some energy or it absorbs some energy. Can't really do both. So as we get to labeling this, we're going to label the reactants and the products, and then either the energy being released or absorbed in this reaction. So I'll walk through this one with you. And I'll kind of help explain it to you. But if you want to take a shot at it yourself, which I would encourage you to do, use your diagrams, use the things you've already labeled, pause me for just a minute and take a minute and see if you can fill in the reactants and products, and then decide whether energy was released or absorbed, and fill in either C or D somewhere on your graph. Okay, take a minute to do that, pause me, and I'll wait for you. You didn't pause me, did you? That's terrible of you. How can I ever trust you again? Seriously, pause me. You're still sitting there waiting. All right, if you pause me, thank you. If you didn't, shame. Everybody knows your name except I don't know your name, so I won't ridicule you next time I get a chance. But what I want you to do is label on your picture then, if you haven't already, the reactants, products, and one of those last two choices. Well, the reactants are what we start with. So A, if we're going to label the picture here, A would be our reactants, would be found over here at the beginning of the curve. B, the products would be found at the end. So notice it doesn't matter whether we go from lower to higher like we do in this picture, or if we go from higher to lower. The reactants will always be read as being on the left, the products on the right. So if this was sort of a reaction for A plus B to make C plus D, kind of our generic equation here, then it would look something like this. So A and B are over here on the left, C and D are over here on the right. That's kind of the idea. And through the middle is the action of the reaction going through this curve. So the question then is this a drawing showing energy released or absorbed? Hopefully you came up with energy being absorbed. And again, the reason being you started with less, you were down here when you began, and you ended with more, you were up here when you ended. The difference in those two would be that change in enthalpy. That's the amount of energy being absorbed in this reaction. Okay, and we would, again, as we called it in the notes last week, this is our change in chemical stored energy, or the fancy word for that is enthalpy. So don't be scared with the word enthalpy, scary looking a foreign word sometimes, but delta H, change in H. H stands for enthalpy. It has to do with sort of stored chemical energy in the bonds of the compounds. So in this case, we can tell that we've gained energy. What it didn't ask us to do was label the activation energy at all, which is kind of the size of this hill as it relates to the beginning amount of energy and the peak of the hill. But we'll be getting to plenty of those as it goes on. Okay. Now, I'm not going to work through all of the questions that are in this particular page with you. I'm going to let you try some of these. The first few are relatively simple. It will ask you to come back to this drawing a bit. Question 2 and question 6 will both ask you to consider the same diagram again. So you'll be using it again. But what I do want to do is jump to a question down a bit further and go through one of these drawing pictures with you where you have to sort of synthesize the picture from scratch. And I'm just going to work through one of these with you, I think. Maybe I'll do a second one, but I would encourage you just to watch the first one and then try working on the other ones by yourself. You're certainly welcome to watch both of them if I go through a couple of them for you here, but maybe go through one with me and then certainly try the other one on your own, or even better, pause me now and work on 19 for a few minutes and then come back and watch and see if you filled it in more or less correctly. So I'll give you the opportunity to do that again. Go ahead and pause me if you'd like to try 19 by yourself. Okay, I'll work through 19 with you here. So there's a couple of hints. One is that it's an endothermic reaction. It's important that you're able to recognize very, very early on here, if you don't already know, that an endothermic reaction is like one that we just looked at, where we start with less energy and we end with more. So starting with less, ending with more. And we don't know what the pathway is, but in general, it's going to be something like that. So this is endothermic. Exothermic would show us starting high and ending up lower because we've released some energy. So this is the general shape of an endothermic reaction. Start low, go high. Now, that's the shape. It also tells us the activation energy. So that's telling us the size of the hill. And remember, the activation energy is always the size of the hill from the start of the reaction to the peak of the highest point in that hill. So there's our activation energy, right? But it also tells us an ending energy of 375. So ending energy is going to be over here, 375. So I'm going to scale my graph. I need to put some numbers on here. We're working with numbers for the first time. I'm going to scale it as such. Basically make every little dashed line worth 50. You don't need to number all of those, but we want to probably number like every 100. And then we'll have room enough for all the data on this graph. You can scale 17, 18, and 19 in this way. It should fit. Question 20, you can scale actually quite a bit closer up, zoomed in, and it'll actually fit a little bit nicer. So it says it has an ending energy of 375. Again, that's the ending amount over on the product side of the reaction. I'm going to go ahead and just kind of draw in roughly that I know my reaction is going to end at around 375. So that's the ending amount at 375. And this is in kilojoules. Notice that's that energy unit we've been seeing in all of our thermochemistry reactions so far. Joules sometimes, but usually kilojoules. It says there's a change in energy or enthalpy of 75 kilojoules. So that's our change in energy. From start to finish of the reaction, there's a change of 75. And because we know this is endothermic, it means we started lower and we're ending up higher. Specifically, we're starting lower and ending up higher by 75 because it says the change in energy is 75 kilojoules. This means I started at 300, okay? And I ended 75 higher than that at 375, and that was given in the problem. So it didn't tell me we started at 300, at least not directly, but I can figure that out because it ends at 375, and it's an endothermic reaction that's gaining 75 kilojoules of energy. Now, the other thing it told us is the activation energy size. And now that we have our starting point drawn, we can actually draw on the activation energy. We need a hump here from the starting point on the left, the peak of the hill, that is 200 kilojoules in size. So we're going to start at 300 and go up by 200 kilojoules to the peak of the mountain here at 500. So I'm going to kind of draw that in. And then you can just draw in your curve however you like. Something like that. It's going to reach all the way up to 500 and then come down and stop dropping again at 375, about like so. So far, this accomplishes what it gave us so far. It's endothermic. It starts low and goes high. It's got an activation energy of 200 from my starting point at 300 to my peak at 500. That's a 200 kilojoule activation energy. It has an ending energy of 375. We got that. And a change of 75 kilojoules. And that 75 is sort of right here from 300 up to 375. This is our delta H. It didn't ask me to label that, but I'll just go ahead and do it here. Okay, so delta H is 75 kilojoules, and that's given in the problem. Now, it says also to add a second curve. Now, I'm going to switch colors. You can do the same, or you can use a dashed line. Add a second curve that shows the path of a reaction when a catalyst is used and the activation energy is cut in half. Now, the activation energy was 200 before. We're going to cut that in half and make the activation energy only 100. So instead of going from 300 all the way up to 500, we're going to go from 300 up to just 400. So right about here, and then still end up at the same point because the reaction's delta H value does not change when we use a catalyst. So we're going to go up to 400 and then come down to 375. That doesn't give me a lot of a hill at the top here, notice. Just a little bit of a speed bump almost up here. Now the activation energy is still 100 because the activation energy is from this low point to the peak of the shorter hill now. So my activation energy there is showing as 100 kilojoules for the red pathway. Even if I shave that hill down to where it's just a smooth little bit of a bump right there, I'm still going to have some kind of activation energy because I'm starting to lower down over here. So that picture's done. Now, how does a catalyst make a reaction proceed faster? I'm not going to tell you that because that should be in your notes. I want to have you take a swing at answering that one. We did answer this last question. What was the initial amount of stored energy? Because we figured that out to start our question or start our graph at 300. We figured it out from the data that was given in the problem. That since we ended at 375 and we're gaining 75, that means we had to have started at 300. So it's just kind of arithmetic from there. Now, I'm going to work through 20. Again, if you'd like, I'd encourage you now to use what we've done together in 19 and try 20 on your own. And pause me and do that. Take a couple minutes and work through it and then come back and I will pick up with finishing out number 20. So go ahead and pause me if you'd like now. Okay, I'll show you how to work through 20 and hopefully you've taken the time to do that for yourself. This one uses smaller numbers. Now, you don't have to have a sense exactly of how to number things, but notice most of the numbers here are in intervals of 20. So like 80, 80, 60, everything's in 20s. So I'm just going to go ahead and number my graph in 20. So still start at 0, but every line will be worth 20. So I'll number every other line, 40, 80, 120, 160, and then 200 at the top. And I think things will still fit here. You could number the same way we did on the other one, but you'd end up with a very, very short, flat graph, and it's really hard to see detail when you do that. So it's much better if you can stretch it vertically, but still fit it on the page. Okay, this one's exothermic. So we have an exothermic reaction here, which means in general, again, the opposite of what we did in the last one, we're going to start high and end lower, going through some pathway to get there in this sort of a path. So it's going to go from high to low, exothermic. And the activation energy is 80. The initial energy is also 80 kilojoules, and the change in energy is 60. So let's take those one at a time. The initial energy is 80. That means I'm going to start here at 80. It says there's a change in energy of 60. Now, change in which direction? We know it's exothermic, so I need to start higher and go lower by 60. So I'm starting at 80. I'm going to end at just 20. Pretty low here at the end. And then it also says we have an activation energy of 80 kilojoules. So I have an 80 to start with. I have to put in another 80 just to get over the hump. So it means I'm going to go from 80 all the way up to 160 at the peak of this hump here. And then down to the other side of the mountain, all the way down to 20. So we are going to have to add energy in. So even an exothermic reaction requires some energy be inputted, like an investment to get your business started. And then it kind of goes like a roller coaster from there. Once you reach the peak, the idea is you continue on the other side and end up with a graph that looks something like this. This accomplishes what we've been asked to do. Right? It starts at 80, it goes up another 80 in the activation energy, and then it ends up with an overall change in energy of 60. Again, from start to finish, from 80 down to 20 is a 60 kilojoules change. And we'd say 60 kilojoules of energy are released here because we went from 80 down to 20. It's like you spent 60 bucks. You started with 80, now you get 20. But it also asks us to add a second curve. So I'm going to switch colors again. Second curve that shows the path of reaction when the catalyst is used and the activation energy is reduced by 75%. So remember, our initial activation energy was 80 kilojoules, and that's the size of the hill, like here. Okay, that's our activation energy of 80. We're going to shrink that down by 75%. So we're going to take off 3/4 of that. So only 1/4 of it will be left. Right? You're going to take 75% away from 80. Well, hopefully you can think about that as a fraction. take away 3/4 of 80 and you'll be left with only 1/4 of 80. And 1/4 of 80 is a 20 kilojoule activation energy. So hopefully you figure that out and kind of makes sense. You're only going to have an activation energy of 20. So our little hill is only going to go up to this point, okay, here. So the same starting point, I'm going to come along, go up to just a smaller activation energy of 20 kilojoules, and still end up down here in the same place we wound up before. Say a shorter pathway. Activation energy here is only 20. So it was an 80 kilojoule activation energy. Now it's only 1/4 of that teeny tiny little activation energy here. We've reduced it by 75%. So that's our picture. That's the drawing. Two different pathways there. You can do it in colors. You can do the second one in a dashed line, whatever you like. What is the activation energy with a catalyst? We just kind of answered that. We figured it out at 20 kilojoules. And what is the final amount of stored energy in both of these? Okay, in both of these problems, the final amount of energy is the amount here at the end of the problem. So that's still 20. Now those are different 20s, it turns out. The activation energy of 20 is measured here. Okay. The final amount of stored energy is simply reading off the bottom of our curve across to this point on the left, and that puts us at 20 kilojoules. So 20 kilojoules from two different places on this graph. So that leaves you 17 and 18. They're a little simpler. 17 is a little simpler, and 18 is a lot like these. What I'd like you to be working on is at least finishing up all of the first page where we have questions that are fill in the blank, and all that last page where we have those drawings to finish. And in between, you have some short answer questions, 12, 13, 14, 15, 16. Makes you think a little bit about your understanding so far about activation energy, collision theory, and remember collision theory, simply the stuff that starts this out from our notes from last week, 3 things that have to be true for reactants to form products, for a reaction to occur. So look back at that, refer to that in your notes. If you don't have this in your notes, you should put it there because it's really important you understand collision theory for a number of things in this current unit. Not only what we're doing here, but things into next week too. So that gives you an idea kind of how to start with this page. And gives you some ideas of the answers. I'll have the answers for you, and we'll discuss some questions that you might have next week to check. But you want to finish this up all through number 11 and the very last 4 here at a very minimum, and you should tackle the short answer questions in between. Don't be afraid to be wrong. I'd much rather you take a stab at your answer than be afraid to make mistakes. So be brave, take a shot at some of those short answer questions. And it doesn't have to sound fancy or be complete sentences. Just give me what you think you understand so far. And we'll have you share that. We'll talk about it. And we'll polish your answers up next time I see you, which will be next week. See you then.